You may not drink it directly, but contaminated mining water finds its way into our ecosystems, our food chains, and our water resources, threatening the safety of both people and the environment. Across the United States, abandoned mines have leaked toxic runoff into nearby streams for decades. The biggest culprit of this pollution is something called acid mine drainage. Acid mine drainage occurs when leftover minerals from mining operations reacts with oxygen and water, creating highly acidic contaminated water. This runoff, rich with heavy metals, flows through our environment, polluting surrounding ecosystems and threatening public health, especially underserved and marginalized communities.
Over the course of a year, our team was challenged with designing a passive water treatment system that used fungi to remove heavy metals from mining-influenced water. Our system was designed to be low maintenance and capable of handling a flow of 10 gallons per minute. It targets the removal of heavy metals commonly found in mining runoff, such as arsenic, copper, manganese, zinc, aluminum, and iron. In order to be successful, our system had to meet EPA discharge standards, run without electricity, and be practical for remote and rural locations. This process flow diagram shows our passive treatment system for acid mine drainage. First, the acid mine drainage enters the limestone pond, where pH is increased and aluminum and iron precipitate out as metal hydroxides. Once the water flows through the limestone pond, it will enter a series of packed bed columns. These columns are filled with encapsulated dried fungal biomass, and as the water passes through these columns, metals are absorbed onto the fungal media.
In order to minimize fungal media waste and reduce the need for constant replacement of our columns, we designed an off-site regeneration process for once the columns reach breakthrough. The columns are transported to an off-site facility where the regeneration cycle begins. Concentrated sulfuric acid is circulated through a 3-column system to desorb the metals, followed by a DI water rinse, a caustic rinse for neutralization, and a final DI rinse. The resulting waste solution, now containing the recovered heavy metals, is stored in a hazardous waste tank for later disposal.
To support our design, our team conducted a series of batch experiments where we used the fungi species Fusarium. The goal of these experiments was to evaluate how effectively the fungi removed heavy metals from the mining-influenced water. Heavy metal ions bind to the surface of the fungal cell through a process called biosorption, which is a surface-level interaction where metals attach to functional groups on the cell wall. This mechanism allowed us to quantify how much metal the fungi could remove from solution, and those results directly informed the design of our passive treatment system.
For our experiment, with the guidance of Dr. Sherry DeVore, we cultivated a Fusarium species in a malt extract broth for 5 days. The resulting fungal biomass was then thoroughly washed and dried at a low temperature for 9 days. Once dried, the biomass was ground into a fine powder and introduced to a synthetic mine-influenced water solution containing arsenic, manganese, zinc, and copper, mimicking the heavy metal composition of acid mine drainage. We tested 2 pH values to identify the optimal pH for sorption, which helped determine the target pH of our effluent exiting the limestone pond. Aqueous samples were collected at 10 different time points to monitor and calculate the amount of metal adsorbed, assuming metals no longer in solution had adsorbed to the biomass. With the known values of the volume of solution, the fungal biomass, the initial heavy metal concentrations, we were able to determine the best fit isotherms and biosorption capacities. Additionally, we analyzed the adsorption kinetics by identifying both the reaction order and the rate of metal uptake. Our experimental results exhibited low biosorption capacities, with coppers being the largest at 7.8 milligrams per gram biomass and a pseudo-second order rate. Zinc was found to have a biosorption capacity of 2.4 milligrams per gram biomass and a pseudo-first order rate. The remaining metals showed negligible absorption.
We utilized MATLAB software and the convection diffusion equation to model the change in metal concentration over time through the packed bed column. We utilized the finite difference method, iterating over time and distance to create a breakthrough curve. This allowed us to determine when the biomass was exhausted.
Unfortunately, our experimental results for Fusarium species demonstrated a slow reaction rate and low adsorption capacity. Because of these results, our MATLAB model determined that a 16-kilometer long column would be required for a 2-week maintenance period. Although this result is unreasonable, we believe our design has great potential for a different sorbate or aqueous metal composition.
Since our experimental results gave us unrealistic design parameters, we scaled the system down to a much smaller flow rate and used kinetic values and bioabsorption capacities from literature. This gave us a 2.5 meter long column with a breakthrough time of 1 week. While more manageable, this is still a pretty large column for a low flow. Still, fungi continue to show strong potential for heavy metal removal, and researchers have found ways to enhance their bioabsorption capacity through things like iron oxide coatings.
To estimate the total cost for a passive treatment system, we considered both one-time construction as well as reoccurring operation and maintenance expenses. The system startup cost was approximately $900,000, which includes excavation, liner installation, construction of treatment units, and fungal biomass preparation. Annual operation and maintenance costs of our system are estimated around $100,000 per year. This includes materials like caustic and acid for regeneration, the energy it takes for drying the fungal biomass, and routine labor costs of the passive treatment system. Compared to traditional treatment systems that operate actively, these operational costs are actually much lower. Research of active treatment systems show operational costs that equal around $500,000 per year. This would make our passive treatment system around 80% cheaper to maintain and operate.
The experimental process was full of challenges, including contamination issues, difficulties with drying methods, and discrepancies in the ICP-MS measurements. Statistical analysis of experimental results showed poor fits for kinetic models, leading to inconclusive findings. We suspect this is partly due to the inaccurate ICP-MS readings. We hypothesized that copper was the primary metal absorbed due to its high concentration and the limited amount of biomass available. The scarcity of surface sorption sites may have also prevented significant absorption of the other metals.
While working through this experiment, we directly followed the mining water composition provided by our test document. Because of this, we failed to consider other constituents commonly found in acid mine drainage. Compounds like potassium, magnesium, and calcium, which would influence the aqueous chemistry and bioabsorption capacity. Therefore, the results from this experiment will not reflect how the design would perform in the natural environment. In future studies, conducting a bench-scale column reactor experiment using a metal solution with the common constituents will allow for a more accurate representation of this design.
The use of bioabsorption for heavy metal removal and passive treatment is still a largely unstudied area, which made our design particularly challenging, especially when trying to apply fungal biomass to the harsh conditions of acid mine drainage.
All of our experimental work and funding was made possible through the support of Dr. Sherry DeVore and her laboratory, and we're incredibly grateful for their guidance throughout this project.